This video teaches us how to determine the rotational inertia for an object that is rotating about a point other than its center of mass. Naturally, objects do spin around that center of mass point, but they can be forced to rotate about a different point depending on the other objects that are attached to them, or by simply inserting a pivot point and causing them to rotate around a fixed axis. Let's recall the formulas that we've talked about before that describe the way to calculate inertia for something other than a system of particles. Recall that we have formulas for a thin rod or a solid disk or a hollow sphere and so forth. And so we have to be aware of the need to use these sorts of formulas in our work. A quick review of how to do that for an object like this. Here we have a steel rod with a certain mass and length, and if we want to determine what its rotational inertia is around its center of mass, we would need to know or look up the formula for a thin rod, which is the mass of the rod, the full length of the rod from end to end, squared, and then divided by 12. And so in this case, we would likely change to standard units, 0.2 kilograms, 0.9 meters, and determine our value. Notice the units for rotational inertia are kilogram meters squared. But again, what would we do if instead of the rod pivoting around its middle point, what if it pivots around its end point? Maybe again it's on a hinge or something like that, or maybe this is a sword that somebody is holding on the end point. There are many situations where an object does not pivot around its center of mass. Well, in order to handle this, what we do is we add a factor of m times h squared to the original formula. And the mass in that little factor is the full mass of the object, and then the h is the shift distance. So you can see from the diagram here, if we are pivoting it at a point slightly to the left of the center of mass, the distance, the shift between the center mass point to the new pivot is what we call h. This idea is called the parallel axis theorem, and it describes how if you change the axis point to a different axis that is parallel to the original to the center of mass axis, you need to add this correction factor of mh squared. This is something that's not given to you on formula sheets, so you need to memorize this relationship. This idea applies to any of those shapes on the formula sheet. So for instance, if I had some sort of a disk that was pivoting around a point other than its center, the h value again would be measured from the center of that disk to the new pivot point. I would just use the, maybe if this is a disk, the 1/2 mr squared formula instead. So let's take a look at an example here. So here we have a 150-gram rod, length of 80 centimeters, and we are asked to determine the rotational inertia about this other point P. And it is 10 centimeters from the end. Okay. Well, first of all, that 10 centimeters is not the value that we need. The distance we need is between point P and the center of mass point, between the new axis and the old axis. And so we will use 30 centimeters as that value of h within the calculation. It's the shift. So you can see here that we calculate the rotational inertia of the rod as if nothing had changed, as if it was centered about or rotating about its center of mass. So the full mass of 0.15 kilograms, the full length of 0.8 meters into the 1/12 formula. But then we add this extra correction factor. And notice that the correction factor has nothing to do with whether it's a rod or a sphere or a disk. It is just mh squared. There's no extra fraction. But again, it's the full mass times that shift squared. Always have to make sure we square that distance so we have consistent units throughout. And so we have a slightly greater rotational inertia than we would have if it were rotating about its center of mass, because more of the mass now is further away from the pivot. So the inertia is greater. It's harder for this object to rotate. Let's take a look at another example. Here we'll look at a solid disk, and we'll look to see how the shift of its pivot point affects it. So here we have a diagram that sort of represents this situation. A hole has been drilled halfway between the edge and the center, so that's represented by point P. And we are going to answer this question just in terms of variables. There are no values. We're looking kind of for a formula that maybe we could use in a more general situation. So the distance that we need, that shift distance, is 1/2 the radius of the circle of the disk, and so that's what we'll use within our formula. So we'll start by looking up or recalling that a solid disk's inertia about its center mass is calculated using 1/2 mr squared. And then we will add this correction factor of mh squared, where h is half the radius. A little bit of algebra, and we can see that we develop a factor of 1/4 really in that correction factor, and then adding a half and a fourth, we see that for this object now, we would use a formula of 3/4 mr squared to determine its inertia.